Okay, welcome to my physics lecture series, Chapter 5, Forces in Motion. So if you're not familiar with what's going on here, I'm going through the table, the base outline for the textbook Halliday, Resnik, Walker, 9th edition, college-based, calculus-based physics. I'm in Chapter 5. So far we've done measurements, motion in one dimension, vectors, and motion in two dimension. And now we get to the real meat of it all, and that's forces in motion. And I want to go ahead and start off and talk about this. Newton versus Aristotle. It's a really big important idea. Aristotle. Okay, so with that we have Newton's laws of motion. We'll call it N1, N2, and N3. And I want to talk about this. So let's just I'm not gonna write stuff down. I want to just talk. So let's just talk. Let's see if I have this. Yeah, there we go. We're just going to talk. It's just me and you. We're talking. Okay, so this goes all the way back to Aristotle, the Greek philosopher. I don't remember the actual dates, but a long time ago. And Aristotle had the ideas about motion and physics with one big problem with the way a lot of the Greeks did stuff, and that they would say, okay, let's take something and let's assume it to be true, because it's just obviously true, right? If I drop a rock, it falls faster than a feather. That's obvious. So we don't have to worry about experimenting whether things fall faster or slower or whatever. Heavier things fall faster. It's obvious. We don't need to do that. And from that, we can deduce a bunch of things that come from that. So one of the things that Aristotle said was that if you let something go, it's going to return to its natural position. And that includes motion, right? So if I take an object and I push it, and I stop pushing it, it's going to return to its natural state. Its natural state, the natural state of an object is to be at rest. If you leave it alone, it'll be at rest. If you interact with it, then it will move. So the harder you push it, the faster it moves. And that relates to gravity too, but it's really about forces in motion. The idea that forces make things do what they don't want to do. When you leave them alone, they stop. And it makes sense, right? If I take a chair and I push it, the chair is going to stop when I stop pushing it. Anything that you see when you stop pushing it, it's going to stop. And so that's Aristotle. Then Newton came along with data from Galileo. Galileo was important here too. Galileo took these balls and let them roll down a track. And then he decreased the angle until it's just barely inclined. And that ball would roll along at a constant speed without anything doing to it. And then Galileo came up with the idea, well, in a perfect situation, I don't have a perfect situation. In a perfect situation, that ball would move at a constant speed on a horizontal track. And so it got to the idea that we have an imperfect system. We always have friction involved. And if you could get that friction out, then it would just move along at a constant speed. It's a big deal to talk about Aristotle, because if you talk to any other people in the world, 87.3% of them are going to say if you push on something and you stop pushing on it, it stops. No force, no motion. Force, motion. And in fact, the answer is that forces don't make things move. Forces make things change their motion. Change is the important thing. So let's talk about Newton's first law. So Newton's first law is basically Aristotle was wrong. That's exactly what that says. He says, no, wrong. Newton's first law often says for every, it says for if you, I'm trying to think of the common way to say it. Basically, an object will move in a straight line at a constant speed unless there's a force acting on it. That's what it says. So it really says the natural state of an object is constant speed and direction, which is constant velocity. So no force, constant velocity. That's what that says, which is the opposite of what Aristotle said. Okay. Now, Newton's second law, I'm going to write that down in just a second. Newton's second law says that there is a relationship between the force you apply to an object and its rate of change of velocity, which we call acceleration, and that proportionality constant is mass. So the greater the mass, the less rate of change of velocity. for the same force. And you can see that that's the same thing as Newton's first law, right? Because Newton's first law says no force, no acceleration. And Newton's second law says F net equals ma. It's the same thing. But if you think about the first law as saying Aristotle is wrong, and then you can see why it's there. And finally, the third law. The third law says that forces come in pairs. I want a string. Here's I didn't prepare. It's the same thing as saying this is a cable, but imagine I have a string. Strings come in pairs. Ends of strings come in pairs. If I cut this, I'm still going to have two ends, right? So that's one way to think of it. The other analogy for Newton's Newton's third law is that forces are an interaction between two objects, always between two objects, just like distance is between two objects. There's a distance between Los Angeles and New York. And it doesn't matter if you're going from New York to Los Angeles or Los Angeles to New York, the distance is the same. The direction's different, but the distance is the same. Okay, so that's what Newton's third law says. And we'll look at that in more detail. So let's look at, there's one other thing. An inertial reference frame is in this chapter. And this is the special case. This says that Newton's second law, F net equals ma, only works if you're measuring acceleration with respect to a reference frame that's at rest. And we call that an inertial reference frame. So what's a non-inertial reference frame? So if you get in a train car and there's no window so you can't see outside, and the train car is accelerating, and you try to use Newton's second law, it's not going to work. Okay? Or you won't think it will work. You could make it work. If you get in an elevator and you push the up button and it accelerates up, Newton's second law doesn't work if you're measuring reference accelerations in that frame. Okay. Gravity is actually kind of weird. We like to say gravity is force, but some would say it's just another reference frame, and that makes sense too. But that's not really covered in this course. So what we do is try to always have a reference frame that's not accelerating. It can be moving, it just can't be accelerating. Okay, and that's an inertial reference frame. Okay, so let's go over Newton's second law, Newton's third law, and then some special forces, and then free body diagrams, and then I'm going to show you a Python program. Yeah, it's a lot. Well, we're having fun though, right? Okay. Okay, back to the paper. So let's write Newton's second law. It looks like this. F net equals ma. That's one way to write it. There's another way to write it, but I think this is the way that most textbooks do it, so we'll keep it like this. So let's just imagine that I have, say, a rocket in space. There's my rocket, and it has thrusters on it. And so it has a thrust right here, F1, and then it has another one right here, F2. And so then I could take the sum of those forces. I could say F net is F1 plus F2, and that would be mass times acceleration. So then I could find the acceleration. And really, you're going to get two kinds of problems in introductory physics. You're going to get ones where you know all the net forces and you find the acceleration, and then you'll get ones where you know something about the acceleration and you find the net force. The most common version of this that you'll see is this. F net equals 0. So this says that the net force in an object is 0. We call this equilibrium. It doesn't mean it's at rest. It means it's not accelerating. We call this equilibrium. And you'll notice that I have 0 with an arrow over it because that is the 0 vector. The 0 vector looks like this. 0 x hat plus 0 y hat plus 0 z hat. And it's different than 0. Because if I just say f net equals 0, that's a vector and that's a scalar, and it can't be that case. 0 vector, it has to be 0 in all 3 dimensions. And in fact, we can write this as a 3-dimensional equation, or we could even write it as 2 dimensions. We don't always need the z direction. So I could say this, f net equals ma. I could write that as just 2 scalar equations, and we often do. F net x equals mass times acceleration in the x direction. F net y equals mass times acceleration in the y direction. Now, I do want to point out one other thing. Sometimes you'll see this as this. The sum of the forces is mass times acceleration. And that's the same thing. I don't like this way just because no one wants to write the summation symbol. F net's much easier. You also may see this. F equals ma. That's wrong, right? Because it's not force is mass times acceleration unless there's only one force. It's the net force. You might also see this on a t-shirt. Wrong. Okay, because that doesn't include the vector form of it. I'm going to actually give you some examples with free body diagrams in a little bit. But let's talk about some of the most common forces that you're going to see. Really, there are two types. There are calculated forces. And this isn't usually covered in the book, but it is important. And then there are constraint forces. Calculated forces have an equation. So the first one that you'll see is the gravitational force. On the surface of the Earth, F, they'll call it Fg, and it'll be mg, like that. And here, G is the gravitational field. On the surface of the Earth, G is 0 x hat minus 9.8 y hat, and then 0 z hat, and it has units of newtons per kilogram. So when we talk about forces, it has units of newtons, where 1 newton is a kilogram meter per second squared. So a newton per kilogram is meters per second squared, and that does give you an acceleration. So we saw that G in the two-dimensional motion chapter, and I just want you to know where it is. When we write just G, it's really the magnitude of G, which is 9.8 newtons per kilogram. So be careful about that. It's not negative 9.8. Okay, it has a negative y component, but G is negative. G is, the magnitude is 9.8. Okay, so that's really the only calculated force you'll see. You may see some chapters will include the better form of gravity. It looks like this. I'm going to write it down. I'm not going to explain it just in case. I like to call this F big G. If you're not near the surface of the Earth, it's equal to negative G m1 m2 over r squared. That's a squared. R hat. So this is the interaction between two masses. One of those could be the Earth, doesn't have to be. And G is the gravitational constant. But if you don't have that in here, that's fine. I just wanted to show you that there are other equations of calculated forces. Now, what's a constraint force? Well, a constraint force, the best one is the normal force, N. And you can write it as a vector if you want. So let me give you an example of the normal force with a free body diagram. Let's suppose that I have a table and I put a box on there, and that box has a mass of 1 kilogram. So what forces are acting on this box? I know that there is a gravitational force on there. So this is your second free body diagram. A free body diagram represents an object and all forces acting on that object. We typically draw this as a dot. You can draw the dot off of the side, but the dot from where the forces are. Now, in a later chapter, we'll consider the actual location of where those forces are applied for rigid objects. But here, we'll just assume the whole object's a dot. So I know that I have the gravitational force pulling down. I'll call that Fg, like that, because down towards the center of the Earth. The other thing I know, remember I said this, F net equals ma, and either you know something about the forces or something about the acceleration. In this case, we know something about the acceleration. If it's just sitting on the table, then a is 0 meters per second squared. Again, there's that 0 vector. So if that's true, then the net force has to be the 0 vector. If the net force is a 0 vector, then we have to have some force pushing up, and that force is the normal force. And we don't have an equation for it. It depends on the situation. The normal force is the interaction between two surfaces, and it's perpendicular to the surface. It's always perpendicular to the surface. I'll show you an example where it's not up. Okay, that's a big thing. a lot of people say N equals mg. In this case, the magnitudes are the same. That is true. And they'll say N is in the y direction. Okay, those are common, but not absolutely true. It depends on the situation. So this is a force of constraint. Why is this a force of constraint? So let's say this is, I'm going to use G equals 10, just so I don't make an error. So this is going to have a magnitude of negative, or it's going to have a force negative 10 y hat, right? Negative, it's 1 times 10 in the negative y direction. So this is going to have a force of 10 y hat. So in that case, F net would be N plus Fg, right? Even though it has a negative component, I'm still adding up the forces. So that would be 10 y hat plus negative 10 y hat equals 0 y hat, which is the 0 vector. Okay, so it all works. But now suppose that I take my finger, 1, 2, 3, 4, okay, I got four fingers, and there's my thumb, and I push down on it. So now I have an extra force pushing down of, let's say, 5 newtons. So when you have forces in the same direction, you could do it 2 ways. I'll do it both ways. You could do it this, 5 Newton y hat negative. We'll call it FP, the push force. Or you could do it like this. There's my first force, Fg, and then here's Fp. You can add it on the end. And then you can see what's going to happen. If the block stays on the table, the only way for that to happen is for the normal force to increase. Because these forces still have to add up to 0. So in this case, I have 10 down and 5 down. So N would be equal to 15 y hat newtons. It'd have to increase. So you see the same box, really, same floor, but the normal force is not constant. It's a force of constraint. It says, I'm going to do, it doesn't actually say this because forces don't talk, but if forces could talk, it would say, I'm going to do whatever it takes. I'm going to do whatever it takes to prevent that from going down or up, right? Because now suppose I take away this hand. If this stayed at 15 and the downward force is 10, then it would be a net force of 5 up and the block would accelerate up, and that doesn't happen. So this just does whatever it needs to do to prevent the block from accelerating. It constrains it to the surface. Now, of course, it can only do that for so long. I mean, if you push down with a force of 5 million newtons, maybe that table is going to break. It can't push up with an infinite amount of force. Okay, but that's the normal force. The other force that's very similar is the tension. And we use T. So if I have a string with a mass, then I'd have Fg pulling down and T up. And they don't have to be equal, right? I mean, this tension is such that it says I'm going to pull whatever I need to make sure that this string doesn't change length, which even though it technically does change a little bit, but that's fine. So there's 2 things. The tension always pulls, strings don't push, and it always pulls in the direction of the string. So if I have this mass over here, the T would be in the direction of the string, and this would be Fg down. And so these could not add up to 0, and so it would accelerate. And we're going to do this problem later, but this is a pendulum. Okay, there's another constraint force. It's called friction. So let's go back to our block. So it's a 1 kilogram block. G is equal to negative 10 y hat newtons per kilogram. Just for today, because I don't want to use a calculator or make a mistake. You'd be surprised how much you can make mistakes on a simple paper when you're making a video. So I have the downward gravitational force, Fg. I have the upward normal force of equal magnitude in this case, like that. Now I'm going to take my hand, I'm going to draw it upside down. Like that. And I'm going to push with a force Fp this way of 1 x hat newtons. Suppose you do this and you push with 1 newton, and you can actually measure the force on your... I've got a block. Tape right there. That looks better. So I have a block. I'm pushing with 1 newton right now. I'm pushing. I can tell. I can measure forces with my finger, and it doesn't move. Well, if it doesn't move, again, I know something about the motion. I know that A equals 0 meters per second squared. And if that's true, then F net has to be 0. And if F net is 0, these are in the y direction, this is in the x direction. I have to have another force in the x direction. And it has to be pushing this way. And we'll call that F. And this is the frictional force. So in this case, you could write this. F net equals MA equals 0 equals N plus FP plus FG plus FF. And that looks weird. A lot of times you won't see it that way, but this is correct. Okay. So let's write this out in terms of what we know, right? Because I know that N, well, I even know N, and I know, but let's just say N is equal to N y hat, where N is the magnitude. Fg is equal to negative mg y hat. It's in the y direction. Fp, I know that one. It's equal to 5 x hat newtons. And then F friction would have to be, I don't know what it is. Let's call it Fx x hat plus Fy y hat. So it has a component in the x and y direction. I don't know. I'm just guessing. So if I write that out, I get 0 equals n y hat plus 5 x hat. I'm going to leave the units off. That's the push. Fg is going to be minus mg y hat. And then I have plus ffx x hat plus ffy y hat. And that's going to be equal to 0 x hat plus 0 y hat. That's the 0 vector. So I know that I can just take all these x components together and group them, and the y components together. So if I look at all the x's together, I have 5, and then I have plus ffx. Those are only 2, have to be equal to 0. And then I have in the y direction, I have n minus mg minus, plus Fy equals 0. But I know that n is equal to mg, because if it's not pushing, it never changes if I don't push it. So this has to be 0. So it has to be. And then Ffx would be negative 5 newtons in the x. So then the friction force would be negative 5 newtons. But what if I push harder? What if I push with, I had 1 newton. I changed that. 1. Okay, let's just change this to 5. That's kind of high, but that's fine. So what if I push with 6 newtons? Well, then the same thing has to be true, but now the friction force has to be 6 newtons in the other direction. And if I push to 7 newtons, it has to be negative 7. So you can see how it goes. And it turns out that there is a relationship that these two have to be equal to each other up until some point. If I keep pushing, it's eventually going to accelerate. And it accelerated because it went from not moving to moving, so it had to have a change in velocity. Okay, so it turns out that there is a relationship for the magnitude of this force. The magnitude of the friction force is less than or equal to some coefficient times the normal force. This is our model for friction. This says that if I increase the normal force, one way is by pushing down harder, then I can push this way even harder before it moves. Increasing the contact force between the two surfaces is going to increase the maximum friction force. But also this less than or equal to thing says that this. If I push with 5 newtons and it doesn't move, I don't get the maximum backwards pushing friction, or it would have a net force this way. It constrains that force to whatever it has to be in order to make the net force equal to 0. That's why this is called static friction. It doesn't mean that the two surfaces don't move. It means they don't move relative to each other. So you could put this on the back of a pickup truck and the truck could accelerate even. And as long as these two surfaces aren't sliding, then you do static friction. Once it does slide, there is a friction force also. And it looks like this. We'll call it FK equals mu K in. So mu S is the coefficient of static friction. And then mu S is the same thing, kinetic friction. And they have no units, right? Because this is in newtons and that's in newtons. You can't have any units there. These coefficients depend on the two types of materials interacting. Wood versus paper would have a particular coefficient of friction. Wood versus wood would have a different coefficient. Velcro on Velcro, that one's kind of hard. Typically, it's between 0 and 1. And also typically, the kinetic coefficient is less than the static coefficient. Typically. Okay. It doesn't depend on the contact area. This is just a model, right? A model that we know is wrong. But it works really well. There are situations where this model fails and doesn't work, but this one's much easier. Okay. I'm going to, I think this is a 26-minute video. Should I do the Python thing now? Yeah, let's just do it. Let's do an example, and I'm going to use Python because if this takes forever, it takes forever. I don't want to break it into two pieces. Let's look at the following situation because it'll be fun. So here I have a block on an inclined plane at some angle theta, and it's just sitting there. It's stationary. Let's draw a free body diagram for this because it'll be good practice. And then what I'm going to do, let's say it has a mass of 1 kilogram. So in this case, we can draw the free body diagram. So the first force I have is the downward gravitational force. So let's call this the x direction and this the y direction. It doesn't really matter. Sometimes we'll put x and y this way, but that's fine. So I have the downward gravitational force, mg. A lot of times people write this as mg. Sometimes they write that as fg. So remember, fg is equal to mg. It happens so often, people just I put mg all the time. It's probably a bad idea. I haven't done Newton's third law. Okay, let me set this up and then I'll do Newton's. This is going to be a long video. Long video, this is long, right? That's fine. Then I have the normal force. Notice that it's perpendicular to the surface. I'm not going to do the Python. I'm going to set this up. I'm going to do Newton's third law, and then maybe I'll make a Python as a later video. And you can see if this is at rest, such that A equals 0 meters per second squared. There's no way these two forces can add up, right? This has an x, a y component only, and this has an x and a y component only. So if there's nothing in the x direction to counteract the x component here, so this can't be a free body diagram. We have to have another force, and that force would be this, the frictional force. So I can say F net is N plus mg. It's plus, remember g has a negative component, but it's plus FF equals 0. Now, if you want to write that in terms of the x direction, x and y components, we're going to need a little trick here. So this angle right here is theta, right? Because this line and that line are parallel. And this angle has to also be theta. This line right here is also theta. There's some geometry here. I don't want to go over all the geometry, but it comes up a lot. So let's say F net x. It's going to, what force is in the x direction? Well, I have a component of the normal force. It's this right here. So if this is the angle theta and that's the normal force, that's going to be N sine theta. And then I have a component of the frictional force. It's going to be equal to minus FF cosine theta. You'll notice that this one uses cosine and that one uses sine. So be careful about how you find these components. Look back at the chapter on vectors. And those are the only two forces in the x direction, so they have to add up to 0. In the y direction, F net y, I have the vertical component of this, which is going to be in cosine theta. And then I have the downward gravitational force, mg. So right here you can see that I can solve for n. N equals mg over cosine theta. I don't even know what I'm doing here. I can put that up here. Let's say I want to find the friction force. That's what I'm going to do. I'm going to find the friction force. So if I put that in and use it in this equation, I could say F friction cosine theta equals n sine theta, which is going to be mg over cosine theta times sine theta. And then I can solve that for the friction force, which you would never do, but I did it. Mg sine theta over cosine squared theta. I don't know why I did that. That gave me the magnitude. Okay. Okay, let's do one last thing, Newton's third law, and then we'll call it a wrap. This one went a lot. There's a lot in this chapter. There really is. Don't think, oh, it's just one chapter. It's really a third of the course. That's just a third of the course in this one chapter. So suppose I have two blocks. I'll call this one A and B. And they're pushing against each other. Let's say I have some external force FP pushing right here. And they're in space, so there's no ground. So let's draw free body diagrams for both these. So I know that they're stuck together, but they're not stuck. They're just pushing on each other. So for A, I have the push force. But clearly, B has to do something too. And in fact, there is a normal force between these two because there's a surface. So they would be like this. I'm going to write this as N, B, A. This is the force of block B pushing on block A. And it looks like that. Now, if I go to block B, I know that forces come in pairs. So yes, if something's pushing on block A pushes back. But I don't really care about that. I care about the motion of these two blocks. So if I draw the forces on this one, it's just going to look like this. N, A, B. And you'll notice that the length of this and the length of that are the same. They're the same forces. What you don't want to do is say, oh, well, look, this force pushes on that block. It doesn't. A pushes on B and B pushes back on A. You have to be very careful. I have some examples of this, but it is important to make sure that you only include forces on this that are acting on this. Really, I like to think of, other than calculated and constrained, I like to think of two types of forces: long range, contact. So if it's not a long range force, which really the only one you've seen so far is gravity, it doesn't have to touch. Any other forces acting on block B have to touch it. Whatever this is, if it's a finger, it's not touching B, so it can't exert a force on that. So you can't include that. So always think about what forces are long range and what forces are contact. And if it's not contacting, it's not a force in there. If you put these labels always B on A and A on B, you make sure that you don't put F, this should be P on A. You don't put that on B because it's acting on A. Okay, I don't think I did the best job with Newton's third law. We're going to have to just practice with that. Let me remind you a couple things as I end up this lecture, which is way longer than I normally do. One, playlist down below if you want to look at the other things. Number two, and I've said this before, this is not going to cut it. Physics is complicated. Okay, I've been studying physics for a really long time, and I still get things wrong. It takes practice. Don't think that I didn't get it right away, I'm not smart enough. You can do physics. You can do it. Okay. It just takes time. all things that are fun take time. If I want to play the piano, I have to practice the piano. I can't watch someone on YouTube playing a piano and then play the piano. Maybe there's that one person that did, but for the most of us, most normal humans don't do that. You don't just get it, okay? You have to practice. So don't be afraid of the struggle. Accept the struggle. That's part of the learning process. And keep at it. You can do anything if you keep working at it. I'm almost positive of that. Okay, so I will move on to chapter 6. And I'm not working any example problems just yet. I can go back and do examples later. And maybe I'll post a video about free body diagrams in Python just because it's fun, but I'm not sure. So, okay, I'll stop right there.